We're on lesson 4 of chapter 7, which is exponential growth functions. First, we're going to write a function rule, then we're going to compare graphs of exponential functions, then we're going to solve a real-world problem. So far, we've been working with linear functions, which is y equals m times x plus b, or the slope times x plus the y-intercept. Now we're going to switch it up a little bit. We're going to do exponential functions. That is, y equals a times b to the x power. So in this case, our variable moves to the exponent here. This will only work if a is not 0, because if you multiply anything times 0, it's going to be 0. B needs to be greater than 0, and then b can't be 1. And this will make a little more sense later on. Linear functions, for example, which would be y equals 3 times x plus 2, have a slope of 3, meaning that for every 1 you go up on x, you're adding 3 to y. You notice how every single time it adds 3 as you go up 1. Exponential functions, on the other hand, follow a different rule. Here we see we have y equals 2 times 3 to the x. So 2 is the a, and then 3 is the b to the x power. Now you'll notice that it goes up by the b value, except being multiplied now. It gets multiplied by 3. And if you look actually what we're doing with the x's, that would make sense. At first we have 3 to the negative second power, so that's 3 to the negative second power is 1/9. 2 times 1/9 would be 2/9. Then we have 3 to the negative first power, which is 1/3. 2 times 1/3 is 2/3. Then we have 3 to the 0 power, which is 1. So 2 times 1 is 2. Then we have 3 to the first power, which is 3. 2 times 3 is 6. Then we have 3 to the second power, which is 9. 2 times 9 is 18. And if you think about it, every time we go up a power, we multiply it by 3 again, or one more time. So if x was 3, 3 to the third power is 27. 2 times 27 is 54. And then we would multiply by 3 again, and that would be correct. So we'll be able to spot exponential functions because they're going up by multiplying instead of adding. So first we need to write a rule for these functions. So first let's determine whether it's linear or exponential. Remember, we're adding if it's linear, we're multiplying if it's exponential. Well, these are going up one at a time, so that'll make it pretty easy. Here we're adding 2, we're adding 4, so it must not be adding. So let's check multiplying. Doubling times 2 times 2 times 2. So this will be an exponential function. The first thing we can solve is that a value. Remember, for this one, the a value was 2. And we could figure that out because when x was 0, which made this value 1, we could figure out what times 1 equals 2, which is just 2. So in this case, with our y equals a times b to the x, when the x is 0, the b to the x value is only 1. What times 1 equals 8? And that's pretty simple, right? That's 8. So we know our a value equals 8. So y equals 8 times b to the x. Well, what is this b number here? Well, if you look at here, the b value was 3, and it was going up by 3 because you're multiplying it by 3 each time. Well, what is this going up by? Well, this is getting multiplied by 2, by 2, by 2, and by 2. So in this case, the b would be 2. Y equals 8 times 2 to the x. If you want to plug in a number just to try it out, we have y equals 8 times 2 to the first power, which is just 2. 8 times 2 is 16. 8 times 2 to the second power would be 8 times 4, which is 32. So this seems to work out just fine. Now let's try this one. We have our y equals a times b to the x. So when x is 0, b to the x is going to be 1. So what times 1 equals 27? Well, that's 27. So y equals 27 times b to the x. And this is going up by 3's, it looks like. We're multiplying times 3. So then b would be 3. So y equals 27 times 3 to the x. We could test our answer too. Let's try negative 2 for x. So 3 to the negative second would be 1/9. 27 times 1/9 would be 27 over 9, which would be positive 3. So that would work. So here we're actually going to chart out some exponential functions and we're going to graph them. It says graph the functions of y equals 3 times 2 to the x and y equals negative 3 times 2 to the x. Compare each graph with the graph of y equals 2 to the x, so without an a value. Well, let's actually solve these then. We have y equals 2 to the x, so y equals 2 to the negative second in this case. 2 to the negative second is 1/4, so that's what we'll write. Now we have 2 to the negative first. 2 to the negative first is 1/2. We have 2 to the 0, which is 1. We have 2 to the first, which is just 2. And 2 to the second, which is 4. So if we're going to plot this out, we'd have negative 2 and 1/4, negative 1 and 1/2, 0 and 1, 1 and 2, 2 and 4. If you notice here, if we're going to graph this then, we can see a curved line forming. I'm going to do my best to create this curved line. So starting around here and working our way up like so. And this is what exponential functions look like. It's going to increase at an ever faster pace, and eventually it's just kind of going to look like a straight line going up and down because it's increasing so quickly. Let's look at this then. 3 times 2 to the x power. Well, 2 to the negative second is 1/4, times 3 would be 3/4. Next we would have the negative first. So 2 to the negative first is 1/2. 3 times 1/2 is 3/2. Or that would be just 1 and 1/2, or 1.5. Now we have 3 times 2 to the 0. Well, 2 to the 0 is 1, so 3 times 1 is 3. Now we have 3 times 2 to the 1, which is 2, so that would be 6. Then we have 3 times 2 to the second, which is 4, so that would be 12. So you notice what this 3 did is we multiplied all the regular answers, 2 to the x times 3. 1 becomes 3, 2 becomes 6, and 4 becomes 12. So if we're going to plot this out then, we have negative 2 equaling 3/4. We have negative 1 equaling 1.5. We have 0 equaling 3, 1 equaling 6, and 2 is going to be off the screen at 12. So if we plot this one out, it'll look somewhat like that. And we see that it just increases that much faster because of the 3. Now we have negative 3 times 2 to the x. So 2 to the negative second power we see is 1/4 times negative 3 is negative 3/4. 2 to the negative first is 1/2, so times negative 3 is negative 3/2, or negative 1.5. 2 to the 0 power is 1, so negative 3 times 1 is negative 3. 2 to the first power is 2, so negative 3 times 2 is negative 6. Then 2 to the second power is 4, so negative 3 times 4 is negative 12. So watch what happens when we plot this one out. We have negative 2 and negative 3/4. We have negative 1 and negative 1.5. We have 0 and negative 3. 1 and negative 6. And 2 and negative 12 somewhere way down here. So if we plot this one out, it's going to look something like this. And you see this is going the absolute opposite direction as this blue line. That's because it's the negative 3 that does that. It makes it go in the opposite direction. You could actually call this a reflection across the x-axis because it's actually a mirror of this one because of that negative number right here. Both of these, though, are a stretch of 3 compared to this one. These dots are always going to be 3 times as high as the other ones here. We're going to use what we've been learning so far to apply it to a real-world situation. So it says the owner of a 1953 Hudson Hornet convertible sold the car at an auction. The owner bought it in 1984 when its value was $11,000. The value of the car increased at a rate of 6.9% per year. It says write a function that models the value of the car over time. This is very similar to the things we've been doing so far, but we're going to follow this model to solve these kind of problems. So in this case, the A becomes the initial amount that something is. 1 plus the rate of increase becomes your B, and then t for time becomes your x variable, that is your exponent here. So in this case we have y equals A times 1 plus the rate to the t. The rate was 6.9%. If we're going to write that as a decimal, that would be 0.069. So then we have a times 1 plus 0.069. 1 plus 0.069 is 1.069. And then that's going to be raised to the t for time. So here's our function, y equals a times 1.069 to the t. Remember, a is the initial amount now, and that was this much. So our function then would be y equals the initial amount, which is 11,000, times our rate plus 1, so 1.069, raised to the time for t. Because every year it's going to be multiplied times the rate. So if t was 3 years, you would multiply it times the rate 3 times, or 1.069 times itself 3 times. If it was 5 years, you would multiply this times itself 5 times. So that's why time is the exponent. It says the auction took place in 2004. What was the approximate value of the car at the time of the auction? It says round your answer to the nearest dollar. Well, how long was it since he bought it? 2004 and 1984, that's 20 years. So we can replace that t with 20. 11,000 times 1.069 to the 20th power. 1.069 to the 20th power then, if I do that on my calculator, would come out to about 3.79799. Then we can multiply that times the 11,000. And that would give us an answer of 41,777.9. So to the nearest dollar, I would go $78. So that's about how much this person sold that car for when he bought it for $11,000, because it was going up by 6.9% each year.